before anything we can recognize as space, before time had meaning in any familiar sense, there existed a condition so extreme and so compressed that every law of physics as we know it begins to break down when we try to describe it. The universe did not begin as a structured place filled with stars and galaxies. It began as an unimaginably hot and dense point where all energy, space, and matter were contained in a state of singularity. There was no distance, no direction, no up or down, no past or future in the way we understand them today. Everything that would ever exist was compressed into something smaller than anything we can physically compare it to in the modern universe. Then, in an instant that defies all human intuition, expansion began. This moment of expansion is what we refer to as the Big Bang, but it is not an explosion in space like a bomb going off. It is the expansion of space itself. Space did not exist prior to this moment in any meaningful sense. Instead, space and time emerged together as the universe began to stretch and cool. In the earliest fraction of a second, the universe expanded faster than the speed of light. This rapid inflation smoothed out the structure of the cosmos and laid the foundation for everything that would come later. Tiny fluctuations in energy during this period would eventually become the seeds of galaxies, stars, and planets. As the universe expanded, it began to cool. This cooling was essential at the beginning. The energy density was so high that no particles could exist in stable form. Everything was pure energy. But as temperatures dropped, energy began to convert into the first fundamental particles. Quarks and electrons appeared, the building blocks of all matter. Quarks combined to form protons and neutrons. And within minutes of the universe's existence, the first simple atomic nuclei began to form in a process called nucleosynthesis. These early nuclei were mostly hydrogen and helium, the simplest and most abundant elements in the universe. Despite this progress, the universe was still a very different place from what we observe today. It was completely opaque. Light existed, but it could not travel freely because it constantly scattered off charged particles. The universe was like a dense fog of plasma, glowing but not transparent. For hundreds of thousands of years, light was trapped in this fog, bouncing endlessly without traveling in a straight line. During this period, the universe continued expanding and cooling, gradually becoming less dense. Eventually, a critical moment arrived, known as recombination. At this stage, the universe had cooled enough for electrons to combine with nuclei to form neutral atoms. This may sound like a small change, but it transformed the entire nature of the cosmos. Once atoms formed, light was finally able to travel freely without constant interaction with charged particles. The universe became transparent for the first time. The light released during this moment still exists today as a faint glow filling all of space. We observe it as the cosmic microwave background radiation, a silent echo of the early universe that provides some of the strongest evidence for the Big Bang theory. After the universe became transparent, there was still a long period before the first stars existed. This era is often called the Cosmic Dark Ages. Despite its name, it was not empty, but it was dark, because there were no light sources yet. The universe was filled mostly with hydrogen and helium gas, slowly drifting under the influence of gravity. Over time, gravity began to play a more dominant role. Even though matter was spread out fairly evenly, tiny fluctuations in density existed everywhere. Some regions had slightly more matter than others, and gravity began pulling material into these denser areas. This is where the true story of cosmic giants begins. Gravity is the invisible architect of the universe. It is the force that transforms chaos into structure. Over millions of years, regions of slightly higher density continued to attract more and more matter. Gas clouds grew larger and more compact. As they contracted, pressure and temperature at their cores increased. Eventually, in the densest pockets of gas, conditions became extreme enough to ignite nuclear fusion. This was the birth of the first stars. These first stars were nothing like the stars we see today. They were enormous, often hundreds of times more massive than our Sun. Because they formed from a universe that contained almost no heavy elements, they burned hotter, brighter, and much faster than modern stars. Their lifespans were short, sometimes only a few million years, which is brief on cosmic timescales. Yet, during their short existence, they played a crucial role in shaping the universe. Inside their cores, nuclear fusion created the first heavy elements, such as carbon, oxygen, and iron. When these stars died, they spread these elements across space, enriching the universe and preparing it for future generations of stars, planets, and eventually life. As more stars formed and died, they began grouping together under gravity to form larger structures. These structures became galaxies. A galaxy is not just a random collection of stars. It is a vast gravitational system where stars, gas, dust, and dark matter all interact in complex ways. The earliest galaxies were chaotic and irregular, but over time they evolved into more structured forms like spirals and ellipticals. Our own galaxy, the Milky Way, is one such structure, containing hundreds of billions of stars bound together in a rotating disk. Within these galaxies, something even more mysterious began to form. At their centers, matter continued to accumulate in extremely dense regions. Over time, some of these regions collapsed into objects so dense that not even light could escape them. These were the first black holes. A black hole forms when matter is compressed into a point of infinite density known as a singularity. Around this singularity is a boundary called the event horizon. Once anything crosses this boundary, it cannot return. Not even light can escape the gravitational pull. Black holes are not just cosmic vacuum cleaners, as they are sometimes described in simplified explanations. They are complex gravitational engines that shape their surroundings in powerful ways. As matter falls toward a black hole, it forms a spinning disk of superheated gas known as an accretion disk. This material heats up to extreme temperatures and emits vast amounts of radiation before disappearing forever beyond the event horizon. In some cases, black holes can outshine entire galaxies due to the energy released by infalling matter. The formation of these early cosmic giants marked a turning point in the evolution of the universe. From this stage onward, the cosmos was no longer just a uniform expanding gas. It became a structured environment filled with extreme objects that influenced everything around them. Gravity continued to build larger and more complex systems, leading to galaxy clusters, superclusters, and vast filaments of matter stretching across billions of light years. Yet, even as structure grew, much of the universe remained invisible to us. Observations of galaxies revealed something puzzling. The visible matter alone could not explain the gravitational forces holding galaxies together. There had to be something unseen providing additional mass. This unknown substance is what we now call dark matter. Although we cannot see it directly, its presence is inferred through its gravitational effects. Dark matter forms a hidden scaffolding that supports the visible universe. guiding the formation of galaxies and larger cosmic structures. In addition to dark matter, another mysterious force began to influence the universe on the largest scales. This is dark energy, a force that drives the accelerated expansion of the universe. While gravity pulls matter together, dark energy pushes space apart. Over time, it has become the dominant force in the cosmos, determining the ultimate fate of the universe itself. From the initial singularity to the formation of the first cosmic giants, the universe has undergone an extraordinary transformation. What began as a state of pure energy evolved into a vast and structured cosmos filled with stars, galaxies, and black holes. Every step in this process was governed by fundamental forces working across unimaginable scales of time and space. Yet, this is only the beginning of the story. The cosmic giants that now dominate the universe continue to grow, evolve, and interact in ways that shape the destiny of everything within them. The universe is still expanding, still cooling, and still forming new structures. Even now, billions of years after the first stars ignited, gravity continues its silent work, pulling matter together and building ever larger and more powerful cosmic systems. The story of the universe is far from over, and the giants we observe today are only a glimpse of the immense forces that continue to shape reality itself. In the earliest stages of the universe, after matter first began to form and light was finally able to travel freely, there was still no structure on the scale we recognize today. Space was filled mostly with diffuse hydrogen and helium, spread almost evenly, but not perfectly uniform. Those small imperfections in density, almost insignificant at first glance, would become the most important feature of the entire cosmic story. Without them, there would be no galaxies, no stars, no planets, and no cosmic giants. But nature is rarely perfectly uniform, and in that slight irregularity lies the origin of everything we see in the universe today. To understand how structure emerges, we must understand the most silent and persistent force in the cosmos. Gravity is not a force that pushes or pulls in the way we typically imagine everyday interactions. It is the curvature of space-time itself, a bending of reality caused by the presence of mass and energy. In the early universe, where matter was spread thinly across vast regions, gravity still operated relentlessly. Even the smallest increase in density created a gravitational advantage. Over time, matter began to drift toward these slightly denser regions, slowly amplifying the differences that already existed. This process did not happen quickly. The universe, though expanding and cooling, was still relatively smooth for hundreds of millions of years. During this period, matter was mostly invisible to the eye, forming vast clouds of hydrogen gas. There were no stars to illuminate space, no galaxies to define structure, only an expanding darkness filled with potential. Yet, within this darkness, gravity was working continuously, pulling atoms together with infinite patience. The key to structure formation lies in instability. If a region of space has slightly more matter than its surroundings, it exerts a slightly stronger gravitational pull. This causes more matter to fall into it, increasing its density further. This feedback loop is slow at first, but becomes increasingly powerful over time. Once it passes a certain threshold, collapse becomes inevitable. What begins as a barely noticeable fluctuation eventually becomes a massive structure. However, gravity alone is not the only influence. The early universe was also filled with pressure from radiation and thermal energy. These forces resisted collapse, pushing matter outward and smoothing irregularities. For structure to form, gravity had to overcome this pressure. This balance between collapse and expansion defined the pace at which the first cosmic structures emerged. The first major step in this process was the formation of what we call dark matter halos. Dark matter, unlike ordinary matter, does not interact with light or electromagnetic forces. It does not emit, absorb, or reflect radiation. It is invisible, yet it has mass and therefore responds to gravity. Because it does not interact with radiation, dark matter was able to begin clumping together much earlier than ordinary matter. It formed large, invisible scaffolds in space, creating gravitational wells into which normal matter would later fall. These dark matter structures acted like cosmic blueprints. While ordinary gas remained smooth for a longer time due to pressure, dark matter was already forming dense regions and large networks. Over time, these halos grew larger as more dark matter was pulled into them. They became the gravitational anchors of the universe, determining where galaxies would eventually form. As the universe continued to expand, ordinary matter began to follow the paths laid out by dark matter. Hydrogen and helium gas slowly drifted into these gravitational wells. As more gas accumulated, pressure and temperature at the centers of these regions began to rise. Eventually, the density became high enough for cooling processes to become effective. When gas can cool, it loses pressure support, allowing gravity to dominate even more strongly. This is the critical step that leads to the formation of the first stars. But before stars could ignite, the universe had to pass through a complex phase of gradual collapse. Gas clouds did not simply fall directly into stars. Instead, they fragmented into smaller and smaller clumps, each influenced by turbulence, pressure variations, and gravitational instabilities. These collapsing regions varied widely in size and mass. Some would become small clusters of stars, while others would form massive proto-galaxies. During this period, the universe was still largely dark. There were no visible light sources, but the seeds of future brilliance were forming everywhere. The scale of this transformation is difficult to comprehend. Regions of space spanning thousands of light years were slowly collapsing under their own gravity, taking tens or hundreds of millions of years to evolve into the first coherent structures. Eventually, in the densest regions of these collapsing clouds, temperature and pressure reached critical levels. At this point, hydrogen nuclei began to fuse into helium, releasing enormous amounts of energy. This marked the ignition of the first stars. These early stars, often called population 3 stars, were vastly different from modern stars. They contained almost no heavy elements, which meant they could grow much larger before reaching stability. Some may have been hundreds of times more massive than the Sunday. The formation of these stars dramatically changed the universe. For the first time since the cosmic dark ages, light was being produced in large quantities. These stars burned extremely bright, but also extremely fast. Their internal temperatures were so high that they fused elements far beyond hydrogen and helium, creating the first generation of heavier elements in the universe. These elements would later become the building blocks of planets, moons, and eventually life itself. When these first stars reached the end of their lives, many of them died in violent explosions known as supernovae. These explosions were not just destructive events, they were creative forces. Supernovae scattered newly formed elements across space, enriching surrounding gas clouds and changing the chemical composition of the universe. This enrichment allowed future generations of stars to form with more complex chemistry, which in turn allowed for more stable planetary systems. As more stars formed and died, they began to cluster together under gravity. These clusters grew into the first galaxies. A galaxy is not simply a collection of stars. It is a dynamic system where gravity, rotation, gas dynamics, and dark matter all interact. The earliest galaxies were irregular and chaotic, often shaped by rapid star formation and frequent collisions. Over time, however, gravitational forces began to organize these systems into more stable forms. One of the most important features of galaxy formation is rotation. As gas clouds collapse, any slight initial rotation becomes amplified due to conservation of angular momentum. This is similar to a spinning ice skater pulling in their arms to spin faster. As a result, many galaxies begin to flatten into rotating disks. These disks become the familiar spiral structures we observe in many modern galaxies. Inside these forming galaxies, star formation continued at a rapid pace. Dense regions of gas gave birth to clusters of stars, while other regions remained relatively empty. The structure of a galaxy is therefore highly uneven, with bright stellar nurseries coexisting with vast dark voids. Over time, feedback from stars, including radiation, stellar winds, and supernova explosions, began to influence the surrounding gas, regulating the rate of star formation. However, the most powerful influence within galaxies came from an unexpected source. At the centers of many galaxies, matter continued to accumulate into extremely dense regions. Over time, these regions collapsed further, forming black holes. These black holes were not passive objects. As they grew, they began to dominate their surroundings, influencing the motion of stars and gas on enormous scales. The relationship between galaxies and their central black holes is one of the most important discoveries in modern astrophysics. The mass of a central black hole is closely linked to the properties of its host galaxy. This suggests that black holes and galaxies evolve together, influencing each other over cosmic time. In many cases, the energy released by material falling into black holes can regulate star formation, either triggering it or suppressing it, depending on conditions. As galaxies continued to evolve, they did not exist in isolation. Gravity pulled them toward one another, leading to collisions and mergers. These interactions played a major role in shaping the structure of the universe. When galaxies collide, their stars usually do not physically collide due to the vast distances between them, but their gas clouds interact violently. These collisions often trigger bursts of star formation, creating new generations of stars in short periods of time. Over billions of years, these processes led to the formation of large-scale cosmic structures. Galaxies are not randomly distributed throughout the universe. Instead, they form along vast filaments of dark matter and gas, creating a web-like structure known as the cosmic web. These filaments intersect at nodes where galaxy clusters form, while vast empty regions called voids separate them. This structure reflects the influence of gravity acting on both visible and invisible matter across cosmic time. At this stage in the universe's evolution, cosmic giants are fully established. Galaxies, black holes, and massive clusters dominate the landscape of space. Yet even now, the universe is still changing. Gravity continues to shape structures, dark matter continues to guide formation, and dark energy begins to influence the overall expansion of space itself. The story of cosmic giants is not just about the formation of large objects. It is about the emergence of complexity from simplicity. From a nearly uniform sea of particles, the universe has built structures of astonishing scale and diversity. Every galaxy, every star cluster, every black hole is a product of billions of years of gravitational evolution. What makes this process remarkable is its inevitability. Given the initial conditions of the universe, structure formation was not a rare event, but an unavoidable outcome. Gravity ensures that any small irregularity grows over time. The universe is therefore not static or random, but deeply dynamic and structured by fundamental physical laws. As we move forward in this cosmic story, we begin to see not just the formation of structures, but the rise of some of the most extreme objects in the universe. Black holes grow larger, galaxies become more complex, and clusters of galaxies begin to dominate vast regions of space. The universe is no longer a simple expanding gas. It has become a vast and intricate network of cosmic giants, each playing a role in the ongoing evolution of everything that exists. As gravity continued shaping the early universe, the first generations of structure had already taken form. Dark matter halos had merged into larger systems, gas had collapsed into dense regions, and galaxies had begun to emerge as recognizable cosmic cities. But within these early galaxies, another transformation was about to begin, one that would change the entire chemical and energetic nature of the universe forever. This was the birth of the first stars, the original sources of light in a universe that had previously been dark for hundreds of millions of years. To understand the formation of the first stars, it is important to recognize the conditions that made them possible. After the recombination era, the universe was filled mostly with hydrogen and helium gas. There were no heavier elements such as carbon, oxygen, or iron. This absence of metals, in astronomical terms, had a profound effect on how gas clouds behaved. Without heavier elements to assist in cooling, gas clouds in the early universe cooled less efficiently, allowing them to collapse into much larger structures than would be possible today. As a result, the first stars were not small or moderate in size. They were enormous, unstable, and incredibly powerful. Within dark matter halos, gas began to collect in vast clouds, stretching across hundreds of light years. These clouds were not uniform. They contained regions of slightly higher density, and as gravity continued to act, these denser pockets began to contract faster than their surroundings. As contraction continued, the gas heated up. This heating created pressure that resisted collapse, but in the densest regions, gravity eventually overcame this resistance. The clouds fragmented into smaller clumps, each one destined to become a protostar. A protostar is not yet a fully formed star. It is a collapsing ball of gas that has not yet ignited nuclear fusion. During this stage, the object is still gathering mass from its surroundings. As more gas falls inward, the core becomes hotter and denser. The energy released by gravitational collapse is enormous, and it slowly builds the conditions necessary for fusion to begin. However, in the early universe, this process was different from what we observe in modern star formation. Because cooling was inefficient, these protostellar clouds remained relatively large, allowing them to accumulate vast amounts of material before stabilizing. As these protostars grew, they became unstable giants. The temperature at their cores rose to millions of degrees. Eventually, a critical threshold was reached where hydrogen nuclei began to fuse into helium. At this moment, the star was born. Nuclear fusion released an immense amount of energy, creating outward pressure that balanced the inward pull of gravity. This balance is what defines a stable star. However, in the case of the first stars, this balance was temporary and fragile due to their extreme masses. These first stars, known as population 3 stars, were fundamentally different from any stars we observe today. Their composition was almost entirely hydrogen and helium, with virtually no heavier elements. This lack of metals meant that they could not cool efficiently during formation, allowing them to grow to enormous sizes. Some of these stars may have reached masses hundreds of times greater than our Sun. Their luminosity was correspondingly extreme, making them some of the brightest objects ever to exist in the universe. The internal structure of these massive stars was also different from smaller, more stable stars. In a typical star like the Sun, energy is transported from the core outward through radiation and convection over long periods. But in extremely massive stars, radiation pressure becomes dominant. The energy produced in the core is so intense that it pushes outward with enormous force, making the star highly unstable. This instability means that the lifespans of these early stars were extremely short, often lasting only a few million years. Despite their short lives, their impact on the universe was profound. These stars were the first sources of ultraviolet radiation, bathing surrounding space in intense energy. This radiation began to alter the surrounding gas clouds, ionizing hydrogen atoms and creating expanding bubbles of hot plasma. This process, known as reionization, marked another major phase transition in the universe. It gradually transformed the cosmos from a neutral, opaque medium into an ionized, transparent environment. But the most important contribution of the first stars was not their light, it was what they created inside their cores. Through nuclear fusion, these stars began producing heavier elements for the first time in cosmic history. Elements such as carbon, oxygen, silicon, and iron were formed deep within these stellar interiors. These elements did not exist in the early universe before stars. Their creation marked the beginning of chemical complexity in the cosmos. As these massive stars reached the end of their lives, they did not fade quietly. Instead, many of them ended in catastrophic explosions known as supernovae. A supernova is one of the most energetic events in the universe. When the core of a massive star can no longer support itself against gravity, it collapses rapidly, triggering a violent rebound that ejects the outer layers of the star into space. This explosion can briefly outshine an entire galaxy. The material expelled during these supernovae carried the newly formed heavy elements into surrounding space. This process enriched the interstellar medium, changing its composition permanently. Regions that were once composed only of hydrogen and helium now contained the raw materials for more complex structures. This enrichment was essential for the formation of later generations of stars, which would be smaller, longer-lived, and more stable. In addition to supernova explosions, some of the most massive early stars collapsed directly into black holes without a full explosion. These early black holes served as the seeds for the supermassive black holes that would later form at the centers of galaxies. The existence of these early black holes explains how some supermassive black holes in the universe grew so quickly in cosmic time. As the first stars died, they left behind a dramatically altered universe. The once pristine hydrogen and helium gas was now mixed with heavier elements. This changed the way gas clouds cooled and collapsed. With the presence of metals, cooling became more efficient, allowing gas clouds to fragment into smaller pieces. This led to the formation of second-generation stars, which were less massive and more stable than the first. These new stars began to populate early galaxies in large numbers. Star formation became more organized and sustained, rather than dominated by a few extremely massive stars. Galaxies transitioned from chaotic systems of rare giants to structured environments filled with diverse stellar populations. This marked the beginning of long-term galactic evolution. Within these evolving galaxies, star clusters formed in dense regions of gas. These clusters contained hundreds or thousands of stars born from the same molecular cloud. Over time, gravitational interactions within these clusters caused some stars to be ejected, while others remained bound together. This dynamic environment contributed to the diversity of stellar systems observed in the universe today. The energy output from these early stars also had a significant effect on their surroundings. Stellar winds, composed of high-speed particles emitted from the surface of stars, began to shape the structure of nearby gas clouds. Combined with radiation pressure and supernova explosions, these processes created a highly dynamic and turbulent interstellar medium. Star formation was no longer a simple process of collapse, but a complex interplay of feedback mechanisms. In some regions, intense star formation led to what are known as starburst galaxies. These galaxies experienced rapid periods of star formation, producing new stars at extremely high rates. However, this process was self-limiting. The energy released by massive stars eventually heated and dispersed surrounding gas, reducing the material available for further star formation. This feedback loop helped regulate the growth of galaxies over time. As galaxies continued to evolve, they began interacting with one another. Gravitational attraction caused galaxies to merge, forming larger and more complex systems. These mergers often triggered new waves of star formation by compressing gas clouds and disturbing galactic structures. Through repeated mergers, small early galaxies gradually combined into larger systems, eventually forming the massive galaxies we observe in the present universe. At the same time, the role of dark matter remained crucial. Dark matter halos provided the gravitational framework that held galaxies together during collisions and mergers. Without dark matter, galaxies would not maintain their structure during these violent interactions. Instead, they would disperse and lose coherence. Dark matter therefore acted as an invisible, stabilizing force throughout cosmic evolution. By this stage in the universe's history, the first stars had already transformed the cosmos. They had introduced light into darkness, created the first heavy elements, and initiated the chemical evolution that would eventually lead to planets and life. Their brief existence set in motion processes that would continue for billions of years. Yet, even as these early stars faded, their legacy remained embedded in every structure that followed. The elements they created became part of new stars, new galaxies, and eventually planetary systems. Every atom of carbon in living organisms today was once forged in the core of a star. In this sense, the first stars were not just cosmic objects, they were the origin of complexity itself. As we move further into the story of cosmic giants, the focus shifts from individual stars to even larger and more extreme structures. Black holes begin to grow in size and influence. Galaxies evolve into massive systems, governed by both visible and invisible matter. The universe becomes increasingly structured on the largest scales, revealing a cosmic web of interconnected filaments and voids. The birth of the first stars was only the beginning of this transformation. Their light pierced the darkness, but their true legacy lies in the way they reshaped the universe itself. From this point onward, the cosmos was no longer a simple expanding field of gas. It had become a dynamic and evolving system of energy, matter, and gravity, setting the stage for the rise of the most powerful objects in existence. After the first stars ignited and the universe experienced its initial transformation from darkness into light, the cosmos entered a new and far more structured phase of evolution. Stars were no longer rare isolated events forming within vast clouds of hydrogen. Instead, they began clustering together within growing regions of space shaped by gravity and dark matter. These regions were the earliest versions of galaxies, though at the time they were not yet the elegant spiral or elliptical systems we observe today. They were chaotic, irregular, and constantly changing. But within that chaos, the foundation of all galactic structure was being built. To understand how galaxies take shape, we must first understand the environment in which they form. The universe at this stage was still expanding, still cooling, and still influenced heavily by dark matter. Ordinary matter, composed of gas and newly formed stars, was only a small fraction of the total mass of the universe. Dark matter dominated the gravitational landscape, forming large, invisible halos that acted as scaffolding for everything else. These halos were not static. They grew by attracting more dark matter and by merging with other halos, gradually building larger and more massive structures over time. Inside these dark matter halos, ordinary gas continued to fall inward under gravity. As it accumulated, it began to form dense regions where star formation could occur. Unlike the isolated star formation of the earliest epoch, these regions were now embedded within larger gravitational systems. This meant that stars were forming not in isolation, but as part of increasingly complex environments where gravity, motion, and feedback processes interacted on multiple scales. As more gas fell into these halos, it did not simply collapse directly into a single structure. Instead, the gas carried angular momentum, or rotational motion, inherited from the large-scale flows of matter in the early universe. This rotation became extremely important in shaping the final structure of galaxies. As gas collapsed inward, conservation of angular momentum caused it to spin faster and faster, much like an ice skater pulling in their arms. This increasing rotation prevented the gas from collapsing directly into a single point, and instead caused it to flatten into a rotating disk. These rotating disks of gas became the first true galactic structures. Within them, stars formed in large numbers, particularly in dense regions where gas clouds collided and compressed. Over time, these early disks began to resemble the basic structure of modern galaxies, though they were still highly irregular and turbulent. They lacked the well-defined spiral arms and smooth symmetry seen in mature galaxies, but the fundamental pattern was emerging. At the same time, dark matter continued to play a critical role in shaping these systems. The dark matter halo surrounding each galaxy acted as a gravitational anchor, holding the system together and influencing its overall structure. Without dark matter, the rotating gas disks would not have been able to maintain their stability. The visible matter alone did not have enough gravitational strength to account for the observed motion of stars within galaxies. This discrepancy revealed the presence of a vast unseen mass that governed galactic dynamics. As galaxies grew, they did not remain isolated. Gravity caused them to move toward one another, leading to frequent interactions and mergers. These collisions were not gentle events. When two galaxies passed close enough, their gravitational fields distorted each other, pulling out long streams of stars and gas known as tidal tails. These structures could stretch across hundreds of thousands of light-years, connecting interacting galaxies in dramatic cosmic displays. During these interactions, gas clouds within the galaxies were compressed and disturbed. This often triggered bursts of star formation, known as starbursts. In these events, galaxies could produce new stars at rates far higher than normal. The compression of gas clouds during collisions created ideal conditions for rapid gravitational collapse, leading to the formation of massive clusters of young stars. These starbursts were temporary, but extremely important in shaping the evolution of galaxies. As galaxies merged repeatedly over time, they grew larger and more complex. Small, irregular systems combined to form larger disks, while some mergers disrupted disk structures entirely, leading to more spheroidal or elliptical galaxies. The final shape of a galaxy depended heavily on its merger history. Galaxies that experienced relatively calm evolutionary paths tended to develop into spiral galaxies with well-defined disks, while those that underwent frequent violent mergers often became elliptical and more chaotic in structure. Within these evolving galaxies, the distribution of stars became increasingly structured. Dense regions of star formation began to form patterns as gravitational forces and rotational dynamics shaped the movement of gas. In disk galaxies, these patterns eventually developed into spiral arms. Spiral arms are not static structures. They are density waves that move through the galactic disk, compressing gas as they pass and triggering new star formation. As stars move through these arms, they form bright regions that trace the spiral pattern. The formation of spiral arms is a complex process involving both gravity and rotation. As the galaxy rotates, different regions of the disk move at different speeds. This differential rotation stretches and twists density variations, creating spiral patterns. These arms are not permanent structures, but rather dynamic features that constantly evolve as the galaxy rotates and interacts with its environment. In the central regions of many galaxies, matter continued to accumulate into extremely dense concentrations. These regions often contained supermassive black holes, objects with masses ranging from millions to billions of times the mass of the Sun. The origin of these supermassive black holes is still an active area of research, but it is believed that they began as smaller black hole seeds formed from the collapse of early massive stars or dense gas clouds. Once formed, these black holes began growing by accreting surrounding gas and merging with other black holes during galaxy collisions. As material fell toward them, it formed accretion disks that emitted enormous amounts of radiation. In some cases, the energy released by these accretion disks made the central region of the galaxy far brighter than all its stars combined. These active galactic nuclei became some of the most luminous objects in the universe. The growth of supermassive black holes had a significant impact on the evolution of their host galaxies. As they consumed matter, they also released energy in the form of radiation and powerful jets of high-energy particles. These jets could extend far beyond the galaxy itself, heating surrounding gas and regulating star formation. In some cases, this feedback process could suppress star formation by expelling gas from the galaxy, while in others it could trigger new star formation by compressing nearby clouds. As galaxies continued to evolve, they began to organize into larger structures. Groups of galaxies formed clusters, held together by gravity. Within these clusters, galaxies interacted frequently, merging and exchanging material. The space between galaxies was not empty, but filled with hot gas and dark matter, forming a complex environment where gravitational interactions played a continuous role in shaping structure. On even larger scales, galaxy clusters themselves began to align along vast filaments of dark matter. These filaments formed a cosmic web, a large-scale structure that spans the entire universe. In this web, galaxies are not randomly distributed, but instead arranged along interconnected threads, separated by enormous voids. These voids contain very few galaxies and represent some of the largest empty regions in the universe. The formation of galaxies is therefore not an isolated process, but part of a much larger cosmic framework. Dark matter provides the underlying structure, gravity drives collapse and interaction, and gas dynamics shape the visible components. Over billions of years, these processes have transformed the universe from a nearly uniform distribution of matter into a highly structured network of galaxies, clusters, and filaments. Within individual galaxies, the cycle of star formation and death continued to enrich the interstellar medium. Each generation of stars contributed heavier elements to the gas, gradually increasing the chemical complexity of the universe. This enrichment allowed for the formation of planets and more diverse stellar systems. Without galaxies acting as recycling centers for matter, this chemical evolution would not have been possible. The growth of galaxies also influenced the distribution of angular momentum in the universe. As galaxies merged and interacted, they transferred rotational energy between systems. Some galaxies gained spin, while others lost it or changed direction. This complex interplay of motion and gravity contributed to the diversity of galactic shapes and structures observed today. By this stage in cosmic evolution, galaxies had become the dominant visible structures in the universe. They were no longer simple collections of stars, but complex systems governed by multiple interacting forces. Gravity, dark matter, gas dynamics, radiation pressure, and black hole feedback all played roles in shaping their evolution. Each galaxy was a dynamic environment, constantly changing over time. Yet, even as galaxies grew and evolved, the universe itself continued expanding. This expansion gradually pulled galaxies farther apart, while gravitational forces within local regions continued to bind them together. This balance between expansion and gravity determined the large-scale structure of the cosmos. The formation of galaxies marks one of the most important transitions in the history of the universe. It represents the point at which simple matter organized itself into long-lived, complex systems capable of sustaining billions of stars. From the chaotic aftermath of the Big Bang, the universe had developed structure, hierarchy, and diversity on an unimaginable scale. As we move further into the story of cosmic giants, galaxies are no longer the largest known structures in isolation. They are part of a greater hierarchy that includes clusters, superclusters, and the vast cosmic web. Within this structure, even more extreme objects begin to emerge and dominate their surroundings. Black holes grow larger, galaxy clusters become more massive, and the universe begins to reveal its most powerful and energetic phenomena. As galaxies continued to form, merge, and evolve within the cosmic web, one of the most extreme and mysterious objects in the universe began to take shape within their deepest gravitational wells. These objects were not like stars, which shine through nuclear fusion, nor like planets, which reflect or absorb light. They were something fundamentally different, regions of space where gravity had become so intense that the known laws of physics begin to reach their limits. These were black holes, and their emergence marked a turning point in the evolution of cosmic giants. The idea of a black hole begins with a simple but profound consequence of gravity. When a massive star exhausts its nuclear fuel, the outward pressure that once balanced gravity disappears. Without this support, the star's core begins to collapse under its own weight. In smaller stars, this collapse can be halted by quantum mechanical effects, creating white dwarfs or neutron stars. But in the most massive stars, even these forces are not enough. The collapse continues without any known mechanism capable of stopping it. In the final moments of a massive star's life, its core contracts rapidly. Temperatures rise to unimaginable levels, and the structure of matter itself is pushed to its limits. Protons and electrons may combine into neutrons, forming an incredibly dense object known as a neutron star. But if the mass of the collapsing core exceeds a certain threshold, even neutron degeneracy pressure cannot resist gravity. At this point, collapse becomes unstoppable. The core shrinks into a point where density becomes effectively infinite. This is the birth of a black hole. What defines a black hole is not just its density, but the presence of an event horizon. The event horizon is a boundary in space beyond which nothing can escape, not even light. It is not a physical surface, but a mathematical and gravitational limit. Once matter crosses this boundary, it is lost from the observable universe. To an outside observer, it appears as though the object slows down and fades as it approaches the event horizon, never fully crossing it due to relativistic effect. But from the perspective of the infalling matter, the journey continues without interruption toward the center. At the center of a black hole lies a region known as the singularity, where current physics breaks down. In this region, space-time curvature becomes infinite, and the known laws of general relativity can no longer describe what happens. It is a place where our understanding of nature reaches its limit, and where a deeper theory of quantum gravity is needed to fully explain the behavior of matter and space. The first black holes in the universe likely formed shortly after the first generation of stars died. These population 3 stars were extremely massive and short-lived. When they exhausted their fuel, many collapsed directly into black holes without a typical supernova explosion. These early black holes may have ranged from a few tens to hundreds of solar masses. Though small by cosmic standards, they were already objects of immense density and gravitational influence. Once formed, black holes did not remain isolated. In dense star-forming regions and young galaxies, they interacted with surrounding matter in powerful ways. Gas clouds near black holes were drawn inward by gravity, forming rotating accretion disks. As matter spiraled into these disks, it was compressed and heated to extreme temperatures. Friction and gravitational energy conversion caused the material to emit vast amounts of radiation, often outshining entire star systems. This process of accretion is one of the key ways black holes grow. As gas and dust fall toward a black hole, they do not fall straight in. Instead, conservation of angular momentum causes them to orbit the black hole, gradually spiraling inward. As the material gets closer, it moves faster and heats up, releasing energy in the form of X-rays, ultraviolet radiation, and even gamma rays in extreme cases. These accretion disks are among the brightest continuous sources of energy in the universe. In some cases, black holes also produce powerful jets of high-energy particles that are ejected perpendicular to the accretion disk. These jets can travel vast distances, sometimes extending far beyond the host galaxy. They are driven by complex interactions between magnetic fields and rotating space-time near the black hole. These jets can influence the surrounding interstellar and intergalactic medium, heating gas and affecting star formation across large regions. As galaxies evolved and began to merge, their central black holes also came into contact with each other. When two galaxies collide, their stars usually pass by each other without direct interaction due to the vast distances between them. However, their central black holes eventually sink toward the center of the merged system through a process called dynamical friction. As they lose energy through gravitational interactions with surrounding matter, they gradually spiral toward each other. When two black holes come close enough, they form a binary system, orbiting each other at extremely high speeds. Over time, they emit gravitational waves, ripples in the fabric of space-time predicted by Einstein's theory of general relativity. These waves carry energy away from the system, causing the black holes to spiral closer together until they eventually merge into a single, more massive black hole. This merger releases enormous amounts of energy in the form of gravitational radiation, briefly making it one of the most powerful events in the universe. The growth of black holes through mergers and accretion leads to the formation of supermassive black holes, which reside at the centers of most large galaxies. These objects can contain millions or even billions of times the mass of the Sun. Their origin is still an active area of research, but they likely formed through a combination of early massive seed black holes, rapid gas accretion, and repeated mergers during galaxy formation. Supermassive black holes are not just passive objects at the centers of galaxies. They play an active role in shaping galactic evolution. As matter falls into them, the energy released can regulate star formation by heating or expelling gas from the surrounding regions. This feedback mechanism helps control the growth of galaxies, preventing them from forming stars too rapidly. In some cases, this process can even halt star formation entirely, leading to what are known as quiescent galaxies. When supermassive black holes are actively feeding on large amounts of gas, they can become extremely luminous. These active galactic nuclei can outshine the entire galaxy in which they reside. The most extreme examples of these are known as quasars, which can be seen across billions of light years. Quasars represent a phase in which a supermassive black hole is rapidly growing, consuming vast amounts of matter, and releasing enormous energy in the process. The relationship between black holes and galaxies is deeply interconnected. Observations show that the mass of a supermassive black hole is closely related to the properties of its host galaxy, particularly the mass of its central bulge. This suggests that black holes and galaxies evolve together, influencing each other over cosmic time. The exact mechanisms behind this coevolution are still being studied, but feedback from black hole activity is believed to play a central role. Beyond their role in galaxies, black holes also represent fundamental objects in the study of physics. They provide a natural laboratory for testing the limits of general relativity and quantum mechanics. Near the event horizon, time and space behave in extreme ways. Time slows down relative to distant observers, and space-time itself becomes highly curved. These effects make black holes some of the most fascinating and challenging objects to understand in the universe. Despite their name, black holes are not entirely black in a theoretical sense. According to quantum theory, they emit a very small amount of radiation known as Hawking radiation. This process arises from quantum effects near the event horizon, where particle pairs can form and one particle escapes while the other falls in. Over extremely long timescales, this radiation can cause black holes to slowly lose mass and eventually evaporate. However, for astrophysical black holes, this process takes far longer than the current age of the universe. As black holes grew and became more common in the universe, they began to influence large-scale cosmic structure. Their energy output helped regulate the formation of galaxies, while their gravitational presence affected the motion of stars and gas in their surroundings. In some cases, black holes may have even played a role in shaping the distribution of matter in the early universe. Within galaxy clusters, supermassive black holes at the centers of massive galaxies can interact indirectly through their influence on surrounding gas. The hot gas-filling galaxy clusters is often affected by jets and radiation from these black holes, creating cavities and shock waves that can extend over enormous distances. These interactions demonstrate that black holes are not isolated phenomena, but integral parts of the cosmic ecosystem. As the universe continues to evolve, black holes will remain among its most enduring structures. While stars will eventually burn out and galaxies will drift apart due to cosmic expansion, black holes can persist for incredibly long timescales. They represent some of the final stages in the evolution of matter, slowly accumulating mass and eventually evaporating only over times far beyond current cosmic history. The emergence of black holes marks a critical stage in the story of cosmic giants. From the collapse of the first massive stars to the formation of supermassive engines at the centers of galaxies, black holes have shaped the universe in profound ways. They represent both destruction and creation, consuming matter while also driving energetic processes that influence the formation of new structures. As we move forward in the cosmic narrative, black holes will continue to grow in importance. They are not just endpoints of stellar evolution, but central players in the dynamic evolution of galaxies and the universe as a whole. Their influence extends across scales from the smallest regions of space-time to the largest structures in the cosmos, making them true giants of the universe in every sense. At the centers of almost every large galaxy in the universe lies an object so massive, so dense, and so influential that it shapes the fate of everything around it. These are not ordinary black holes formed from single stars. These are supermassive black holes, cosmic giants that can contain millions, billions, and in some cases even tens of billions of times the mass of the Sunday. Their presence is not just a curiosity of astrophysics. It is a fundamental feature of galaxy formation and evolution. Without them, the structure of the universe would look completely different. The origin of supermassive black holes is one of the most important questions in modern cosmology. Unlike stellar black holes, which form from the collapse of massive stars, supermassive black holes require a different growth path. There are several leading theories about how they formed in the early universe. One possibility is that they began as massive seed black holes, formed directly from the collapse of extremely dense gas clouds in the first galaxies. Another possibility is that they grew from the remnants of the first generation of stars, gradually accumulating mass through rapid accretion and frequent mergers. It is likely that both processes contributed to their formation. In the early universe, conditions were dramatically different from what we observe today. Gas clouds were denser, galaxy formation was more chaotic, and star formation occurred at much higher rates. Within these young galaxies, regions of extreme density could collapse directly under gravity, without fragmenting into many smaller stars. Instead of forming a cluster of stars, some of these regions may have collapsed into a single massive object. If conditions were right, this object could bypass normal star formation entirely and form a black hole with a mass far greater than typical stellar remnants. These are known as direct collapse black holes, and they may represent the initial seeds of supermassive black holes. Once these seed black holes formed, their growth began immediately. The universe at that time was rich in gas, and galaxies were still forming and merging frequently. Gas was funneled toward the centers of galaxies by gravitational forces, where black holes resided. As this gas fell inward, it formed accretion disks, releasing enormous amounts of energy. This energy could be so intense that it influenced the surrounding environment, heating gas, and, sometimes, preventing further inflow. Despite this feedback, black holes continued to grow over time, especially during periods of abundant gas supply. Accretion is the primary mechanism by which black holes gain mass. As matter spirals into a black hole, it releases gravitational energy in the form of radiation. This process is extremely efficient compared to nuclear fusion. While stars convert only a small fraction of their mass into energy, accreting black holes can convert a significant portion of infalling matter into radiation. This makes active black holes some of the most luminous objects in the universe. When a black hole is actively feeding at a high rate, the surrounding region can outshine the entire galaxy in which it resides. These active phases are known as active galactic nuclei. When they reach extreme luminosities, they are called quasars. Quasars are among the brightest objects ever observed in the universe. They can be seen across billions of light years, acting as cosmic beacons from the early universe. The energy emitted by quasars comes from matter heated to extreme temperatures as it falls into the black hole's gravitational influence. The accretion disk surrounding the black hole becomes so hot that it emits radiation across the entire electromagnetic spectrum, including visible light, ultraviolet, X-rays, and gamma rays. The existence of quasars in the early universe provides important evidence for the rapid growth of supermassive black holes. Observations show that some quasars existed less than 1 billion years after the Big Bang, meaning that black holes must have grown extremely quickly to reach such large masses in such a short time. This rapid growth suggests that early black holes either formed with large initial masses or experienced periods of extremely efficient accretion, or both. As supermassive black holes grew, they began to exert a powerful influence on their host galaxies. The energy released during accretion does not simply disappear. It interacts with surrounding gas, heating it, and sometimes expelling it from the galaxy entirely. This process is known as feedback, and it plays a crucial role in regulating star formation. If too much gas is heated or expelled, star formation slows down or even stops. In this way, black holes can control the growth of their host galaxies. This relationship between black holes and galaxies is deeply interconnected. Observations reveal a strong correlation between the mass of a supermassive black hole and the properties of its host galaxy, particularly the mass and velocity dispersion of the central bulge. This suggests that black holes and galaxies do not evolve independently, but rather influence each other over cosmic time. The mechanisms behind this coevolution are complex, involving feedback from radiation, jets, and outflows generated by accretion processes. One of the most dramatic ways black holes influence their surroundings is through relativistic jets. These jets are narrow beams of high-energy particles that are ejected from the regions near the black hole's poles. They are thought to be powered by magnetic fields interacting with the rapidly rotating accretion disk and the black hole itself. These jets can travel at speeds close to the speed of light and extend far beyond the boundaries of the galaxy. In some cases, they can influence gas on scales of hundreds of thousands of light years. Jets play an important role in shaping the environment of galaxies and galaxy clusters. When they interact with surrounding gas, they create shock waves and cavities in the hot intergalactic medium. This can prevent gas from cooling and forming new stars, effectively regulating the growth of galaxies on large scales. At the same time, in some regions, jets can compress gas and trigger star formation, showing that their effects are both destructive and constructive depending on the conditions. Supermassive black holes are not static objects. They grow through a combination of accretion and mergers. When galaxies collide, their central black holes eventually sink toward the center of the merged system. Over time, they form binary black hole systems, orbiting each other in a slow spiral. As they lose energy through gravitational wave emission, they move closer together until they eventually merge into a single, more massive black hole. This process contributes significantly to the growth of supermassive black holes over cosmic time. The mergers of supermassive black holes are among the most energetic events in the universe. When two such objects collide, they release enormous amounts of energy in the form of gravitational waves. These waves propagate through space-time itself, carrying information about the dynamics of the merger. Although these waves are extremely weak by the time they reach Earth, they can be detected by sensitive instruments, providing direct evidence of black hole collisions. Over billions of years, repeated mergers and continuous accretion have allowed supermassive black holes to grow to enormous sizes. Some of the largest known black holes contain tens of billions of solar masses. These giants reside in the centers of massive elliptical galaxies and galaxy clusters, where they continue to influence their surroundings through gravity and energy output. Despite their enormous power, supermassive black holes are not infinitely dominant. Their influence is strongest in the central regions of galaxies, where gravity and radiation interact directly with surrounding gas. At larger scales, their effects are mediated through the structure of the galaxy itself and the surrounding dark matter halo. This creates a complex hierarchy of influence, where black holes, galaxies, and dark matter all interact across different scales. In galaxy clusters, supermassive black holes play an even larger role. The central galaxies of clusters often host the most massive black holes in the universe. These objects can influence the hot gas that fills the cluster, known as the intracluster medium. Through jets and outflows, they can create bubbles and cavities in this gas, redistributing energy across vast distances. This helps regulate the cooling of gas in clusters and affects the formation of new galaxies within the cluster environment. The presence of supermassive black holes also affects the long-term evolution of galaxies. Over time, as gas supplies are depleted or expelled, star formation slows down. Many large galaxies eventually become passive systems, with little new star formation occurring. These galaxies are often dominated by older stellar populations and contain massive black holes at their centers that are no longer actively accreting large amounts of matter. Even in their quieter states, supermassive black holes remain important gravitational anchors. They continue to influence the motion of stars in their vicinity and maintain the structural integrity of the galactic center. Their presence is a reminder of the dynamic history of the galaxy and the extreme processes that shaped its evolution. The study of supermassive black holes also provides insight into fundamental physics. These objects exist in regimes where gravity is extremely strong and space-time is highly curved. They serve as natural laboratories for testing theories of general relativity and exploring the limits of our understanding of physics. Observations of their behavior, including accretion, jets, and mergers, continue to provide valuable data for refining theoretical models. As the universe continues to evolve, supermassive black holes will remain among its most enduring structures. While stars will eventually burn out and galaxies will drift apart due to cosmic expansion, black holes can persist for unimaginably long timescales. They represent one of the final stages in the life cycle of matter, slowly growing and eventually evaporating over times far beyond the current age of the universe. The rise of supermassive black holes marks a defining chapter in the story of cosmic giants. From their mysterious origins in the early universe to their dominant role at the centers of galaxies, they have shaped the evolution of cosmic structure on the largest scales. They are both creators and destroyers, regulating the flow of matter and energy across vast regions of space. As we continue exploring the universe, supermassive black holes remain at the center of some of its most profound mysteries. They are not just objects of extreme gravity, but key players in the ongoing evolution of the cosmos. Their influence reaches across time and space, connecting the early universe to the present day and shaping the future of cosmic structure itself. In the vast and evolving universe, not all stellar remnants follow the path of becoming black holes. Some of the most extraordinary objects arise when massive stars collapse under gravity but stop just short of forming an event horizon. These objects are neutron stars, and among them, the most dynamic and observable are pulsars. Though small in size compared to galaxies, neutron stars are among the densest and most extreme forms of matter in existence, representing a state where the fundamental structure of atoms is pushed beyond normal limits. A neutron star is born in the violent aftermath of a supernova explosion. When a massive star, typically between about 8 and 25 times the mass of the Sun, reaches the end of its life, it undergoes a catastrophic collapse. The core contracts rapidly under gravity while the outer layers are expelled into space in a brilliant explosion. In the center, the core is crushed so intensely that electrons are forced to merge with protons, forming neutrons. This process removes the usual atomic structure of matter, leaving behind a dense sphere composed almost entirely of neutrons. The result is an object of staggering density. A neutron star typically has a mass greater than that of the Sun, compressed into a sphere only about 20 kilometers across. This means that a single teaspoon of neutron star material would weigh billions of tons on Earth. Gravity at the surface is so strong that it drastically bends space-time and would crush any known material instantly. Yet, despite this extreme environment, neutron stars are stable, held up by neutron degeneracy pressure, a quantum mechanical force that resists further collapse. Neutron stars are not only remarkable for their density, but also for their behavior. Many of them are born with extremely rapid rotation. As the original star collapses, its angular momentum is conserved, causing it to spin faster and faster, much like an ice skater pulling in their arms. Some neutron stars can rotate hundreds of times per second. This rapid rotation, combined with extremely strong magnetic fields, gives rise to one of the most fascinating phenomena in astrophysics, the pulsar. A pulsar is a type of neutron star that emits beams of electromagnetic radiation from its magnetic poles. These beams are not emitted uniformly in all directions. Instead, they are concentrated into narrow beams that sweep through space as the star rotates. If one of these beams crosses Earth, we observe a regular pulse of radiation, hence the name pulsar. These pulses are incredibly precise, often more accurate than atomic clocks, making pulsars some of the most reliable timekeeping objects in the universe. The discovery of pulsars was one of the most important breakthroughs in modern astronomy. When they were first observed, their regularity was so precise that some scientists briefly considered the possibility of artificial origins. However, it was soon understood that these signals were natural, produced by rapidly rotating neutron stars with intense magnetic fields. The mechanism behind this emission involves charged particles being accelerated along magnetic field lines, producing beams of radiation that sweep across space. The magnetic fields of neutron stars are among the strongest known in the universe. They can be trillions of times stronger than Earth's magnetic field. In some cases, these fields are so extreme that they dominate the behavior of matter near the star. These highly magnetized neutron stars are known as magnetars. Magnetars can produce powerful bursts of X-rays and gamma rays when their magnetic fields undergo sudden rearrangements. These events are among the most energetic phenomena in the galaxy. The environment around a neutron star is equally extreme. Any matter that comes too close is pulled in by intense gravity and often heated to extremely high temperatures before being accreted onto the surface. In binary systems, where a neutron star orbits a companion star, it can pull material from its partner. This process creates an accretion disk, similar to those found around black holes. As material falls onto the neutron star, it releases enormous amounts of energy, often producing strong X-ray emissions. These accreting neutron star systems are important sources of high-energy radiation in galaxies. They serve as laboratories for studying matter under extreme conditions that cannot be reproduced on Earth. The physics governing these systems involves a combination of gravity, quantum mechanics, and electromagnetic forces operating at their limits. Neutron stars also play a crucial role in the production of heavy elements in the universe. While supernova explosions from massive stars produce some heavy elements, the most extreme elements are formed in even more violent events involving neutron stars. When two neutron stars orbit each other in a binary system, they gradually lose energy through gravitational wave emission. This causes them to spiral inward until they eventually collide in a dramatic event known as a kilonova. A kilonova is one of the most powerful explosions in the universe. When neutron stars merge, the collision ejects vast amounts of neutron-rich material into space. In this environment, rapid neutron capture processes occur, known as the R process. This process is responsible for creating many of the heaviest elements in the periodic table, including gold, platinum, and uranium. The debris from these collisions spreads these elements across galaxies, enriching the interstellar medium and contributing to the chemical evolution of the universe. The detection of gravitational waves from neutron star mergers has confirmed many of these theoretical predictions. When two neutron stars collide, they produce ripples in space-time that propagate across the universe. These gravitational waves carry information about the masses, spins, and internal structure of the merging objects. Observations of such events have opened a new era in astronomy, allowing scientists to study cosmic phenomena through both light and gravitational signals. Neutron stars are also important for understanding the limits of matter itself. The interior of a neutron star is one of the densest environments in the universe outside of black holes. The exact composition of matter at these densities is still not fully understood. It is believed that the outer layers consist of a crust of atomic nuclei and electrons, while the inner core may contain exotic states of matter, possibly including superfluid neutrons, hyperons, or even deconfined quark matter. These possibilities make neutron stars a natural laboratory for studying fundamental physics. Despite their extreme nature, neutron stars are relatively small compared to other cosmic giants. However, their influence on their surroundings can be significant. Pulsars, in particular, emit beams of radiation that can interact with surrounding gas and magnetic fields. In some cases, pulsar wind nebulae are formed, where high-energy particles emitted by the pulsar create glowing structures in space. These nebulae are often observed in X-ray and radio wavelengths and provide insight into the interaction between neutron stars and the interstellar medium. Over time, pulsars gradually lose energy as they emit radiation and particles. This causes their rotation to slow down. As they age, their pulses become weaker and eventually undetectable. These older neutron stars may still exist in the galaxy, but without strong emission, they become difficult to observe. They continue to exist as cold, dense remnants of once massive stars slowly drifting through space. In binary systems, neutron stars can undergo further evolution depending on their interactions. If a neutron star accumulates enough mass through accretion, it may exceed the maximum stable mass limit and collapse into a black hole. This transition represents one of the final stages in stellar evolution, linking neutron stars directly to black holes in the cosmic life cycle of matter. The study of neutron stars and pulsars has provided critical insights into many areas of astrophysics. Their extreme conditions allow scientists to test theories of gravity, nuclear physics, and electromagnetism under conditions that cannot be replicated on Earth. Pulsars, with their precise timing, have also been used to detect gravitational waves indirectly and to probe the interstellar medium. On a larger scale, neutron stars contribute to the overall energy and matter cycle of galaxies. Through supernova explosions, kilonova events, and accretion processes, they help redistribute energy and elements throughout the cosmos. They are not isolated remnants, but active participants in the ongoing evolution of galactic systems. As we continue to explore the universe, neutron stars remain some of the most important and fascinating objects for understanding the limits of physics. They represent a bridge between ordinary stellar matter and the extreme conditions found in black holes. They are the dense hearts of dead stars, spinning rapidly and emitting powerful beams of energy across space. In the broader story of cosmic giants, neutron stars and pulsars occupy a unique position. They are not as massive as black holes, nor as large as galaxies, but they embody some of the most extreme physical conditions in the universe. Their existence reveals how matter behaves under conditions of immense pressure, density, and magnetic influence. As the universe continues to evolve, neutron stars will remain as long-lasting remnants of stellar evolution. Some will merge and create new elements, others will collapse into black holes, and many will slowly fade into silence. Yet their legacy will continue to shape the chemical and energetic structure of galaxies for billions of years. The story of cosmic giants is not only about the largest structures in the universe, but also about the most extreme states of matter. Neutron stars and pulsars represent one of these extremes, showing how the death of a star can give rise to objects of extraordinary power, precision, and influence. Across the vast expanse of the universe, there exist objects so luminous that they can outshine entire galaxies. These extraordinary sources of energy are not powered by ordinary nuclear fusion like stars, nor by the steady glow of stellar populations within galaxies. Instead, they are fueled by the most extreme gravitational engines in the cosmos, supermassive black holes consuming matter at incredible rates. When these black holes enter their most active phase, they become quasars, some of the brightest and most distant beacons ever observed. A quasar is not a single object in the traditional sense, but rather a phenomenon that occurs in the environment surrounding a supermassive black hole. At the center of a quasar lies a black hole, millions or even billions of times more massive than the Sun. Surrounding it is a vast accretion disk of gas, dust, and stellar debris spiraling inward. As this material falls toward the black hole, it is compressed and heated to extreme temperatures reaching millions of degrees. In this state, matter does not simply emit light, it emits radiation across the entire electromagnetic spectrum, from radio waves to X-rays and gamma rays. The energy output of a quasar is so intense that it can exceed the combined light of all the stars in its host galaxy. This makes quasars some of the most luminous objects in the universe. Yet, despite their brightness, they are extremely distant and often observed from billions of light-years away. This means that when we observe a quasar, we are looking back in time to a period when the universe was still relatively young. Quasars therefore serve as cosmic time capsules, revealing conditions in the early stages of galaxy formation and black hole growth. The mechanism that powers a quasar is accretion, the process by which matter falls into a gravitational well. As gas and dust approach the black hole, they do not fall straight in. Instead, they form a rotating disk due to conservation of angular momentum. Within this accretion disk, friction and gravitational interactions cause the material to heat up tremendously. The inner regions of the disk closest to the black hole reach the highest temperatures and emit the most energetic radiation. The efficiency of this process is extraordinary. A significant fraction of the infalling matter's mass can be converted into energy, making accreting black holes far more efficient energy sources than nuclear fusion in stars. In addition to the accretion disk, quasars often produce powerful jets of relativistic particles. These jets are launched from regions near the black hole's poles, where magnetic fields interact with the rotating accretion disk and space-time itself. The exact mechanism behind jet formation is still an active area of research, but it is believed to involve complex interactions between magnetic fields and the rotation of the black hole, a process known as the Blandford's-Nayak mechanism. These jets can extend far beyond the host galaxy, sometimes reaching distances of hundreds of thousands of light-years or more. Quasar jets are not only visually striking, but also physically influential. As they travel through intergalactic space, they interact with surrounding gas, heating it and influencing the formation of galaxies in their vicinity. In some cases, jets can trigger star formation by compressing gas clouds. In others, they can prevent star formation by heating gas to the point where it cannot collapse. This dual role makes quasars important regulators of cosmic structure on large scales. The discovery of quasars in the 20th century revolutionized our understanding of the universe. When they were first detected, they appeared as point-like sources of intense radio and optical emission. Their spectra showed unusual features, including extreme redshifts that indicated they were located at vast distances. This meant that quasars were not nearby exotic objects, but extremely luminous sources located in the distant universe. Their brightness implied that enormous amounts of energy were being produced in relatively small regions of space, leading to the conclusion that supermassive black holes must be involved. The realization that quasars are powered by supermassive black holes provided a crucial link between galaxy evolution and black hole growth. It became clear that black holes were not just passive endpoints of stellar evolution, but active and central components of galactic development. During the quasar phase, a black hole is rapidly growing, consuming vast amounts of gas from its surroundings. This growth phase is relatively short in cosmic terms, lasting only tens or hundreds of millions of years, but it plays a critical role in building up the mass of supermassive black holes. Quasars are most common in the early universe, when galaxies were rich in gas and collisions between galaxies were frequent. These conditions provided abundant fuel for black hole growth. As galaxies merged, gas was funneled toward their centers, feeding the central black holes and triggering quasar activity. Over time, as galaxies evolved and gas supplies were depleted or expelled, quasar activity became less common. In the present universe, most supermassive black holes are in a relatively quiet state, no longer accreting large amounts of matter. Despite their rarity today, quasars remain some of the most important tools for studying the universe. Because they are extremely bright, they can be observed across vast distances. This allows astronomers to use them as probes of the intergalactic medium. As quasar light travels through space, it passes through clouds of gas that absorb specific wavelengths. By studying these absorption lines, scientists can map the distribution of matter in the universe and study the composition of gas in regions far beyond the reach of direct observation. Quasars also provide insight into the growth of cosmic structure. The distribution of quasars across space reveals information about the large-scale structure of the universe, including the cosmic web of filaments and voids. Because quasars are associated with massive galaxies and dark matter halos, their locations trace the most massive structures in the universe. This makes them valuable indicators of how matter is distributed on the largest scales. In addition to their role as observational tools, quasars are also important for understanding the physics of extreme environments. The region near a supermassive black hole is one of the most extreme environments in the universe. Gravity is so strong that space-time itself is significantly curved. Time dilation effects become important, meaning that time passes differently near the black hole compared to distant observers. Radiation emitted from the inner accretion disk is highly energetic and often interacts with surrounding matter in complex ways. The study of quasars has also revealed important information about the early growth of supermassive black holes. Observations of extremely distant quasars show that black holes with masses of billions of solar masses already existed less than 1 billion years after the Big Bang. This presents a challenge for models of black hole formation, as it requires very rapid growth from initial seed black holes. Understanding how these early giants formed remains one of the major questions in astrophysics. Several mechanisms have been proposed to explain this rapid growth. One possibility is that black holes formed from the direct collapse of massive gas clouds in the early universe, creating relatively large initial seeds. Another possibility is that early black holes experienced periods of super-Eddington accretion, where they consumed matter at rates exceeding the typical theoretical limits. It is also likely that repeated mergers between black holes contributed to their rapid growth. As quasars evolve, their energy output eventually affects their own growth. The radiation and jets produced by accretion can heat and expel surrounding gas, limiting the amount of material available for further accretion. This self-regulating feedback process helps explain why quasars eventually shut down and transition into quieter phases. Once the gas supply is depleted or expelled, the black hole enters a dormant state, remaining massive but no longer actively growing. Even after the quasar phase ends, the supermassive black hole remains at the center of its galaxy, continuing to influence its dynamics. It may still accrete small amounts of material, producing low-level emissions, but it no longer dominates the energy output of the galaxy. These quiet black holes are often difficult to detect directly, but their presence can be inferred from the motion of stars and gas in the galactic center. On larger scales, quasars play a role in the evolution of galaxy clusters and the intergalactic medium. Their energy output contributes to the heating and ionization of gas in the surrounding environment. This can influence the formation of new galaxies and affect the thermal history of the universe. In this way, quasars are not isolated phenomena, but part of a broader cosmic ecosystem. The study of quasars also connects to fundamental physics. The extreme conditions near supermassive black holes provide a testing ground for theories of gravity, high-energy physics, and plasma dynamics. Observations of quasar spectra, variability, and jet structures continue to provide valuable data for refining theoretical models. In the grand narrative of cosmic giants, quasars represent one of the most energetic and visually spectacular phases in the life of a galaxy. They are brief but powerful episodes in which supermassive black holes reach their peak activity, transforming their surroundings and illuminating the distant universe. Through quasars, we observe the universe not as it is today, but as it was in its most active and formative stages. As we move forward in the cosmic story, quasars begin to fade as the universe evolves. Gas supplies diminish, galaxies stabilize, and black holes settle into quieter states. Yet their legacy remains imprinted across the cosmos, shaping the structure and evolution of everything that follows. As the universe expanded further and cosmic time stretched into billions of years, individual galaxies no longer remained isolated islands of stars drifting alone in space. Gravity, the same force that shaped stars and built galaxies, continued its work on even larger scales. Galaxies began to gather into groups, then clusters, and eventually into some of the largest known structures in the universe. These immense formations are not random collections of galaxies, but highly structured systems bound together by gravity and dominated by the invisible influence of dark matter. This stage of cosmic evolution reveals the universe on its largest observable scales, where matter forms a vast interconnected network known as the cosmic web. To understand galaxy clusters, we must first understand what binds them together. A single galaxy contains billions of stars, but a galaxy cluster can contain hundreds or even thousands of galaxies, all gravitationally bound within a single region of space. These clusters are not just collections of galaxies floating together, they are dynamic systems filled with hot gas, dark matter, and high-energy interactions that span millions of light-years. The total mass of a galaxy cluster is dominated not by visible galaxies, but by dark matter and extremely hot intergalactic gas. Dark matter plays the central role in the formation of galaxy clusters. Just as dark matter halos provided the scaffolding for individual galaxies, larger dark matter structures provide the framework for clusters. Over time, smaller halos merge into larger ones, pulling galaxies into shared gravitational wells. These halos are enormous, extending far beyond the visible boundaries of clusters. The visible galaxies we observe are only small luminous traces embedded within these massive invisible structures. Within a galaxy cluster, galaxies move at extremely high speeds, often thousands of kilometers per second. Despite these high velocities, they remain bound together by the immense gravitational pull of the cluster's total mass. This mass is distributed across three main components: the galaxies themselves, the dark matter halo, and the intracluster medium. The intracluster medium is a vast reservoir of hot gas that fills the space between galaxies. This gas is heated to extremely high temperatures, often reaching tens of millions of degrees, making it visible primarily in X-ray wavelengths rather than visible light. The presence of such hot gas is a key feature of galaxy clusters. It is not simply leftover material from galaxy formation, but a dynamic environment shaped by gravitational collapse, galactic interactions, and feedback from supermassive black holes. As galaxies move through the intracluster medium, they experience pressure and resistance, a process known as Ram pressure stripping. This can remove gas from galaxies, affecting their ability to form new stars. In this way, the cluster environment directly influences the evolution of its member galaxies. Galaxy clusters are also sites of frequent and energetic interactions. While individual galaxies within a cluster are separated by vast distances, gravitational interactions still occur. Galaxies can pass close enough to distort each other's shapes, triggering bursts of star formation or stripping away material. In some cases, galaxies merge within clusters, forming larger and more massive systems. These mergers contribute to the growth of the most massive galaxies in the universe, often found at the centers of clusters. At the center of many galaxy clusters lies a dominant galaxy known as the brightest cluster galaxy. These galaxies are often enormous elliptical systems that have grown through repeated mergers with other galaxies. At their cores, They frequently host some of the most massive, supermassive black holes known. These central black holes can influence the entire cluster environment through their energetic output. Jets and radiation from active galactic nuclei can heat the surrounding gas, preventing it from cooling and forming new stars. This feedback process helps regulate the thermal state of the cluster over long periods of time. The intracluster medium itself is a fascinating environment. Although it is extremely diffuse compared to ordinary matter on Earth, it contains more mass than all the galaxies in the cluster combined. This gas is so hot that it emits X-ray radiation, which can be detected by space-based observatories. The study of this gas provides important information about the total mass and structure of galaxy clusters. It also reveals the presence of dark matter, since the visible mass alone is not sufficient to explain the gravitational binding of the cluster. One of the most important methods for studying galaxy clusters is gravitational lensing. Because clusters contain such large amounts of mass, they can bend light from more distant objects behind them. This bending of light, predicted by general relativity, can produce distorted or magnified images of background galaxies. By analyzing these distortions, scientists can map the distribution of mass within clusters, including both visible and dark matter components. Gravitational lensing has provided some of the strongest evidence for the existence of dark matter in the universe. Galaxy clusters are not isolated structures. They are connected to one another through even larger formations known as superclusters. Superclusters are groups of galaxy clusters and galaxy groups that span hundreds of millions of light-years. However, even superclusters are not the largest coherent structures in the universe. Instead, they are part of a vast network known as the cosmic web. The cosmic web is the large-scale structure of the universe, shaped by the distribution of dark matter and the effects of gravity over billions of years. In this web, matter is not evenly distributed. Instead, it is organized into long filamentary structures that connect dense regions of galaxy clusters. These filaments are separated by enormous voids, regions of space that contain very few galaxies. The resulting structure resembles a vast, three-dimensional web, with galaxies and clusters forming nodes at the intersections of filaments. The formation of the cosmic web began in the early universe, when small fluctuations in density were amplified by gravity. Dark matter played a crucial role in this process, forming the initial scaffolding along which ordinary matter could accumulate. Over time, these fluctuations grew into large-scale structures, with matter flowing along gravitational gradients into increasingly dense regions. This process created the filamentary network we observe today. Within the cosmic web, galaxies do not move randomly. Instead, their motion is influenced by the gravitational pull of nearby filaments and clusters. Matter flows along these filaments toward dense nodes, where galaxy clusters form. This continuous flow of matter shapes the evolution of large-scale structure over cosmic time. The cosmic web is therefore not static, but dynamic, constantly evolving as gravity redistributes matter across the universe. The voids between filaments are equally important in understanding cosmic structure. These regions contain very few galaxies and are some of the most empty spaces in the universe. Despite their emptiness, voids play a role in the overall dynamics of the cosmic web. As matter flows out of voids into denser regions, these empty spaces grow larger over time. This process contributes to the increasing contrast between dense and empty regions in the universe. Galaxy clusters located at the intersections of filaments are some of the most massive gravitationally bound structures in the universe. They act as hubs where matter accumulates from surrounding filaments. These clusters can grow through continuous accretion of galaxies, gas, and dark matter. Over time, they can merge with other clusters, forming even larger superclusters. However, the expansion of the universe eventually limits the growth of these structures on the largest scales. The study of galaxy clusters and the cosmic web has revealed important information about the overall composition of the universe. Observations show that only a small fraction of the universe is made up of ordinary matter, such as stars, planets, and gas. The majority of the universe consists of dark matter and dark energy. Dark matter governs the formation and structure of clusters and filaments, while dark energy drives the accelerated expansion of the universe. As the universe continues to expand, the influence of dark energy becomes increasingly dominant. On the largest scales, it begins to counteract the gravitational attraction between distant structures. This means that while galaxy clusters remain bound, larger structures, such as superclusters, may eventually become isolated from one another over extremely long timescales. The cosmic web, while still visible today, will gradually evolve as expansion continues. Despite these long-term changes, galaxy clusters remain among the most important laboratories for studying cosmic evolution. They contain large populations of galaxies, vast reservoirs of hot gas, and some of the most massive black holes in the universe. By studying clusters, scientists can understand how matter is distributed on large scales, how galaxies evolve in dense environments, and how dark matter shapes the structure of the universe. The cosmic web itself represents one of the most profound discoveries in modern cosmology. It shows that the universe is not random or uniform on large scales, but highly structured and interconnected. Every galaxy, every cluster, and every filament is part of a vast network shaped by gravity and dark matter over billions of years. As we move deeper into the story of cosmic giants, we begin to see how these large-scale structures interact with the most extreme objects in the universe. Supermassive black holes at the centers of clusters influence their surroundings. Hot gas in clusters responds to energy input from galaxies and active nuclei. Dark matter continues to provide the invisible framework that holds everything together. The universe is revealed not as a collection of isolated objects, but as a deeply connected system evolving across unimaginable scales. The formation of galaxy clusters and the cosmic web represents a critical stage in cosmic evolution. It is the point at which the universe becomes structured on its largest scales, revealing the full complexity of gravitational interactions across space and time. From this structure, all smaller systems gain context, and all larger questions about the fate of the universe begin to emerge. As the universe expanded and its large-scale structure became more defined, a deeper and more mysterious layer of reality began to reveal itself. Galaxies formed, clusters grew, and the cosmic web stretched across billions of light years. Yet, observations of these structures led to a profound realization. The visible matter alone could not explain what was happening. Something invisible was shaping the universe on every scale, from galaxies to the largest filaments. This unseen influence was divided into two of the most important mysteries in modern cosmology: dark matter and dark energy. Dark matter is the invisible scaffolding of the universe. It does not emit light, absorb light, or interact with electromagnetic radiation in any detectable way. Yet it has mass, and therefore it exerts gravity. Without dark matter, galaxies would not hold together, galaxy clusters would not form as observed, and the cosmic web would not exist in its current structure. Its presence is inferred entirely through gravitational effects, making it one of the most important but least understood components of the universe. The first clues to dark matter came from observations of galaxies. When astronomers measured the rotation of stars within spiral galaxies, they expected to find that stars farther from the galactic center would move more slowly, since most of the visible mass is concentrated near the center. However, what they observed was very different. Stars in the outer regions of galaxies were moving much faster than expected, at speeds that could not be explained by the visible matter alone. This discrepancy suggested that there must be additional unseen mass extending far beyond the visible boundaries of galaxies. This invisible mass forms what is known as a dark matter halo. These halos are vast spherical regions that surround galaxies and extend far beyond their visible components. They contain most of the total mass of a galaxy, providing the gravitational force needed to hold it together. Without these halos, galaxies would not be stable. Their stars would drift apart over time, and the structures we observe today would not exist. Dark matter is not only important for individual galaxies, it plays a central role in the formation of all large-scale structures in the universe. In the early universe, small fluctuations in density began to grow under the influence of gravity. Dark matter, which does not interact with radiation, began clumping together much earlier than ordinary matter. While normal gas was still coupled to radiation and unable to collapse freely, dark matter was already forming dense regions and large-scale structures. These early dark matter structures acted as gravitational wells. Once the universe cooled enough for ordinary matter to decouple from radiation, gas began to fall into these wells. This process led to the formation of the first stars and galaxies. Without dark matter, the growth of structure in the universe would have been much slower and far less efficient. The entire cosmic web is essentially built upon the framework created by dark matter. Despite its importance, the true nature of dark matter remains unknown. It does not appear to be composed of ordinary atoms. If it were, it would interact with light and other forms of electromagnetic radiation. Instead, it must be made of a different type of particle that interacts primarily through gravity and possibly weak nuclear forces. Many candidates have been proposed, including weakly interacting massive particles, axions, and other exotic particles, but none have been directly detected so far. While dark matter shapes the structure of the universe, another, even more mysterious force governs its ultimate fate. This force is known as dark energy. Unlike dark matter, which pulls structures together through gravity, dark energy drives the accelerated expansion of the universe. It acts as a kind of repulsive effect on cosmic scales, causing space itself to stretch at an increasing rate. The existence of dark energy was discovered through observations of distant supernovae. When astronomers measured the brightness and redshift of these exploding stars, they found that the expansion of the universe was not slowing down as expected due to gravity. Instead, it was accelerating. This was a shocking discovery that fundamentally changed our understanding of cosmology. It implied that some unknown form of energy was permeating space and driving the expansion faster over time. Dark energy is not localized like matter. It appears to be a property of space itself. As the universe expands, more space is created, and with it, more dark energy. This leads to a feedback effect in which expansion accelerates further. Unlike matter and radiation, whose density decreases as the universe expands, the density of dark energy remains roughly constant. This means that over time, dark energy becomes more dominant in the overall energy budget of the universe. The simplest explanation for dark energy is the cosmological constant, a term introduced by Einstein in his equations of general relativity. In this interpretation, dark energy is a constant energy density filling all of space uniformly. However, the true nature of dark energy remains one of the greatest unsolved problems in physics. It could be related to quantum vacuum energy, a dynamic field that evolves over time, or something even more fundamental that we do not yet understand. The interplay between dark matter and dark energy defines the large-scale evolution of the universe. Dark matter pulls structures together, allowing galaxies and clusters to form. Dark energy pushes space apart, driving the accelerated expansion of the universe. At early times, dark matter dominated the dynamics of structure formation. At late times, dark energy has become the dominant force shaping the expansion of the cosmos. On the scale of galaxy clusters and the cosmic web, dark matter is responsible for maintaining structure. It holds galaxies together within clusters and provides the gravitational framework for filaments. Without dark matter, these structures would not exist in their observed form. However, dark energy begins to counteract this structure on the largest scales. As the universe expands, distant clusters and superclusters are gradually pulled apart from one another. This leads to a future in which the large-scale structure of the universe becomes increasingly isolated. Galaxy clusters that are currently connected through filaments will eventually become separated as expansion accelerates. Over extremely long timescales, the cosmic web will fade as structures move beyond each other's observable horizons. In this scenario, each gravitationally bound system will become an isolated island in an ever-expanding sea of space. Within individual galaxies and clusters, dark matter continues to play a central role. It influences the motion of stars, the behavior of gas, and the formation of new structures. Even though it cannot be seen directly, its gravitational effects are essential for maintaining the stability of cosmic systems. Observations of gravitational lensing, galaxy rotation curves, and cluster dynamics all provide strong evidence for its existence. Gravitational lensing is one of the most powerful tools for studying dark matter. When light from distant objects passes near a massive structure like a galaxy cluster, it is bent by gravity. This bending can distort or magnify the images of background galaxies. By analyzing these distortions, scientists can map the distribution of mass within the lensing object. These maps consistently show that there is far more mass present than can be accounted for by visible matter alone, providing direct evidence for dark matter. Dark energy, in contrast, is studied through its effect on the expansion of the universe. By measuring the redshift of distant galaxies and supernovae, scientists can determine how the expansion rate has changed over time. These measurements show that the expansion is accelerating, indicating the presence of a repulsive force or energy component acting on cosmic scales. The combined influence of dark matter and dark energy creates a universe that is both structured and dynamic. Dark matter builds the cosmic architecture, forming galaxies, clusters, and filaments. Dark energy shapes the long-term evolution of this structure, driving expansion and gradually isolating gravitational systems from one another. Together, they determine both the past formation and future fate of the universe. In the context of cosmic giants, dark matter and dark energy are not objects in the traditional sense, but fundamental components of reality that govern how all cosmic structures behave. Every galaxy, every black hole, every cluster exists within a framework shaped by these invisible forces. Without them, the universe would be radically different, lacking the complexity and structure we observe today. As the universe continues to evolve, dark energy will become increasingly dominant. Over time, it will determine the ultimate fate of cosmic structures. Galaxies outside of local clusters will recede beyond the observable horizon. Star formation will slow as gas is consumed or expelled. Black holes will remain as some of the last long-lived structures, slowly evolving over unimaginable timescales. Dark matter, while still essential for local structure, will gradually play a less visible role on the largest scales as expansion separates gravitationally bound systems. Yet within galaxies and clusters, it will continue to provide the unseen scaffolding that holds everything together. The discovery of dark matter and dark energy has fundamentally changed our understanding of the universe. It has revealed that the visible cosmos is only a small fraction of the total reality. Most of what exists is invisible, detectable only through its gravitational or expansive effects. This realization has transformed cosmology into a study not just of matter and energy, but of unseen forces that shape everything we observe. As we continue exploring the universe, these two mysteries remain at the center of scientific inquiry. Dark matter and dark energy are not just abstract concepts, but essential components of the cosmic story. They define the structure, evolution, and ultimate fate of everything from the smallest galaxies to the largest cosmic structures. In the grand narrative of cosmic giants, they represent the hidden foundation upon which all visible structures are built. They are the silent forces shaping the universe on every scale, guiding its past evolution and determining its future destiny.